люди, которые будут готовы делать на них соответствующие открытия.
First of all, and most of all, we need talented young people, because by the time all these installations are launched, we will certainly need new, inspired, and talented young scientists to operate this equipment.
Вы должны подготовить новых талантливых теоретиков, талантливых экспериментаторов, талантливых специалистов, особенно в области информатики, обработки больших данных.
We need to educate new young new theoreticians, young new experimentators, and young new specialists, especially in the sphere of IT and big data.
И, конечно, решить эти задачи возможно только лишь в тесном сотрудничестве ведущих институтов научных с нашими главными, важнейшими университетами, московским, санкт-петербургским и многими другими. Только вместе мы можем решить эту задачу, которая будет иметь важнейшее значение для глобального успеха нашей области науки.
And of course, we will be able to solve this task only if research and scientific institutions help work together with our leading universities, women, Moscow University, St. Petersburg University, and many others. Only in this cooperation, this important task can be solved.
И, конечно, данная конференция, конференция Nucleus 2021, как раз и направлена на решение от подобных задач.
And of course, this conference, Nucleus 2021, is targeted exactly at solving these tasks.
I'd like to thank a translator, which is brilliant translator. So, but let me proceed also in English. I would like to add to what I told. Also, present director, new director of GINR, Grigory Trubnikov, asked me to pass his personal good words and welcome to all the participants of this conference. He would be happy also personally to participate in that, but he is now very busy with our task and cannot do so. So just add my welcome words and his welcome words to this conference. And let me, in conclusion, wish good work, successful work to all the participants of this conference. And of course, I would like to join what Professor Titov told, of course, first of all, to wish all of us and all of our colleagues, all of our participants, good health, good mood, and great new achievements in our very interesting, very progressing science, nuclear physics. So thank you. I wish you success of this conference.
Okay, thank you very much, Viktor Anatolyevich. And from organizing committee and from me, from I think all participants, please accept our congratulations on 65th anniversary of GNR, because as I know, colleagues from GNR were with our conference from the beginning of GNR Foundation, and a lot of important scientific results was obtained in GNR were reported in our conference. And as Viktor Anatolyevich said, the key work is together. We will work and we will see together in one direction. And I hope that the first physics results from NICA Collider, in particular physics results, will be reported in our conference. And happiness, success, and big, big health, of course, for GNR, for our colleagues from GNR. And our present card, it's for you. And so you can see famous faces in this card. And I think all of these famous people participated and reported main scientific results in our conference. Okay. Thank you. And the next speaker is our best friend and our good colleague from CERN. He's a spokesman of ALICE collaboration. It's Luciano Musa. Luciano, can you hear me?
Yes, thank you, Vladimir, dear colleagues and friends. So good morning, everyone. And it is also my great pleasure to say a few words of welcome to the participants of the 71st edition of the Nucleus conference. And I would like to do that by first thanking the organizers, the organizing institutes, so the St. Petersburg State University, the Kurchatov Institute, and the Joint Institute for Nuclear Research. Of course, the co-chairs, the program committee, and the local organizing committee. For their perseverance and the decision to hold the conference, though in a virtual format for the second year. I mean, we just heard that over 71 years, this conference never stopped, and that is really reflects the very high commitment and perseverance of the institutions behind this event. It is obviously unfortunate that for the second time, this prestigious event has to take place in virtual mode. But it is really important that they continue anyway, because the dissemination and discussion of the scientific notions and know-how are really the lifeblood of the scientific basic research. And so somehow the characteristic features of it. And it is actually during these difficult times that society has somehow discovered or rediscovered the centrality of science, as well as our policy-making authorities. And within science, basic research is at the heart, because it is basic research that generates new ideas, the principles, the theories, which may not be immediately applicable or utilized, but nonetheless form the basis of our progress and development in many different fields. And it is clear that we are essentially a very large network. If I take as an example my field of research, so where the focus is really now the mapping and understanding of the QCD phase diagram. So that is really a research that is being attacked from many different angles at many different facilities. From Russia, where the new NICA facility will allow to explore a very large region of the QCD phase diagram, to the very high energy sector, which is being explored at the LXXI and in the US. So now this is the strong message that I would like to convey, especially to the young colleagues attending the conference, and that actually altogether we should convey to the policy makers and to the public, so that science is really at the heart of our progress, not only as mankind, but really the technological progress. And with this, I would really like to conclude my very brief intervention by wishing also from my side and on behalf of the ALICE collaboration to you all a successful and enlightening meeting and conference. Thank you.
Okay, thank you very much, Luciana. Thank you. And I think you can start your presentation, because the next speaker will be from Petersburg Nuclear Physics Institute, and after you presentation, because you told me that you have some meeting in CERN, and you can start now.
Yes, so let me then share my screen.
Yes. Okay.
I think
you
should...
can see, yes, very well.
Okay, very well. All right, so yes, it is my great pleasure to tell you about the ALICE status and future prospects. But before I do that, I would like to say a few quick words about the ALICE collaboration. We are at present about 1,000 signing authors coming from 173 institutes from 42 countries, and Russian institutions and physicists that represents one of the most important contingents of the ALICE collaboration. Now, ALICE started its journey long ago, it's 28 years ago, with actually 9, with the formation of a proto-collaboration to work on the preparation of an expression of interest in 1992. The experiment was approved in 97, and the bulk of the construction and installation took place in the period from 2000 to 2008. And we are taking physics data since 2009, and we, of course, continue till the end of the LXXI run to in 2018. And as you will see, ALICE has still a long and hopefully bright future ahead. Now, the ALICE focus is the study of heavy ion collisions at relativistic energies. Now, as you know, the LHC usually collides protons, but it also smashes together the nuclei of heavy atoms, primarily lead nuclei. And it does so for about 1 month every year, and for a very good reason. That is creating a plasma of strongly interacting colored matter to study fundamental predictions of QCD at the highest temperatures and the densities. So what are the predictions? Well, the QCD, the asymptotic freedom of QCD, let me put this down, suggests that at a sufficiently high temperature, the quarks and gluons behave as quasi-free particles, so essentially traveling independently over large distances and are not localized to hadrons any longer. And we know from lattice QCD that at vanishing biochemical potential, which is the region explored at the LHC energies, and which corresponds to the early universe conditions. There is a continuous crossover around the temperature of about 150 MeV from a hadron resonance gas at low temperatures to a quark gluon plasma at higher temperatures. Now, let me just remark that because QCD is asymptotically free, the thermodynamic quantities, they reach the non-interacting limit, so the limit of a weakly coupled quark gluons system only at extremely high temperatures. So in the range shown in this plot, which is the temperature range that is accessed experimentally, they are below that limit. They are around 20% below from the Stefan Boltzmann values, which is consistent with the picture that has emerged experimentally of a strongly coupled plasma. Now, experimentally, the conditions of high density and temperature, actually largely exceeding the pseudocritical values predicted by lattice QCD, can be realized by colliding heavy ions at relativistic energies, as it is done at the LHC, creating a fireball of actually quite a sizable volume, and with an energy density and the temperature that largely exceed the critical value for the phase transition. Now, the focus of the ALICE experimental program then is the characterization of the properties of the QGP. And this is done with the measurement of a variety of observables that address the various stages of the time evolution of the collision from the early phase when the two colliding charged nuclei pass through each other and produce the high density expanding quark gluon plasma, to the hadronic phase, which precedes the kinetic freeze out of the final state hadrons. Now, the experimental tool is the ELISE detector, which I will not introduce in detail, but I'm just flashing this picture to briefly say that the ELISE detector has a central barrel with tracking, hadron, electron, photon, and jet reconstruction, covering two rapidity units, and a second component, main component, which is a forward muon spectrometer, covering the rapidity range from -2.5 to -4. And then, of course, it's complemented with many other very important detectors, which provide diffractive selection, triggering, centrality, luminosity, and etc. Now, and this is the data we have collected in the first 10 years of heavy ion physics at the LHC, from proton-proton collisions to lead-lead collisions at various energies. So essentially, we have collected about 1 inverse nanobarn of lead-lead collisions and 40 inverse picobarn of PP collisions. And all this, the analysis of all this data resulted in a little over 350 publications so far. Now, it is not my intention to review the results, but I will just show very, very quickly a few recent ones, just to give you a little bit an impression of the breadth also of the different type of measurements that are carried out. And let me start with actually lead-lead ultra-peripheral collisions. So a powerful way of studying the initial stage of the nuclear collision is via ultra-peripheral collisions, in which a photon induced by the strong nuclear electromagnetic field of a nucleus interacts with a quark anti-quark pair from the partonic field of the other nucleus, producing a vector meson like the ρ0, the J-psi, or the psi-2s. And we have performed the measurement of the production cross-section of the J-psi and the psi-2s as a function of rapidity. And from these measurements, then comparing the experimental results with the impulse approximation, so the expected yield in the absence of nuclear effects, we can then extract the gluon shadowing factor, which turned out to be 0.65 at an X value of about 10 to the -3. And that is pointing to a moderate shadowing. Now, this is just to give you an idea of the type of measurements that we perform to try to characterize the initial conditions of the collision. Now, let me move to a completely different topic and show an example on how we try to understand in detail how partons interact with the quark gluon plasma. And one way is by using highly energetic jets, which interact with the QGP medium. And through those interactions, they can lose energy. The jet energy loss is one of the signatures which have been studied with a very high precision, but also their internal structure can be modified. And the modification of the jet internal structure can be used to reveal the physical properties of the QGP itself. So it's a resolving power. Now I'm showing here as an example of the jet substructure measurements that we performed with the ALICE detector using a soft drop grooming algorithm, which essentially provides access to the parton splitting, to the hard parton splitting inside a jet by removing the wide soft angle radiation. So what is measured is the groomed jet radius. We are looking here at charged particle jets reconstructed at mid-rapidity using the anti-KT algorithm with a resolution parameter of R0.2. And what we have found is a narrowing of the scale, the groomed jet radius, theta G, distribution in lead-lead collisions compared to PP collisions, which provides a direct evidence of the modification of the angular structure of the jets in the quark-gluon plasma. And these results compare with a variety of theoretical models of jet quenching, then provide constraints on the detailed jet energy loss mechanism and coherence effects in the quark-gluon plasma. Now, in qualitative terms, now disregarding the details of the modeling, these measurements of the angular structure indicate that the medium has a significant resolving power for splitting with a particular dependence on the angular scale, essentially promoting narrow structures and or filtering out the wide splits in groomed jets, or also wider jets altogether. Okay, so this results demonstrates the sensitivity to the microscopic structure of the QGP, including its angular resolving power. And using very similar techniques, we have also been able to have, for the first time, a direct observation of the Dedekon effect in QCD, which predicts the suppression of the gluon spectrum emitted by heavy quark of mass m and energy E within a cone of an angular size m over E around the emitter. Now, a direct observation of the Dedekon effect in QCD was not possible until very recently, due to the challenge of reconstructing the cascade of quarks and gluons starting from the bound hadronic states. But using new iterative declustering techniques, essentially to reconstruct the parton shower of charm quarks, we managed to make this first observation of the QCD Dedekon effect, which not only confirms a fundamental feature of QCD, but also represents a direct experimental observation of the non-zero mass of the charm quark. So the observables that is measured to reveal the Dedekon is built by constructing the ratio of the splitting angle distribution for D0 meson tagged jets and inclusive jets in different bins of the energy of the charm quark of the radiator. Here I'm just showing the results for the interval 5 to 10 GeV, and which shows very, very clearly the significant suppression in the rate of small angle splittings for the D0 meson tagged jets relative to the inclusive jet sample. And these colored regions corresponds to the Dedekon angles where emission is suppressed. Now let me change completely topic, and now I'm showing here actually measurements with the PP collisions. You know, we do not only study QGP, but also we have a broader QCD program. So we have measured all ground state charm hadrons, mesons, and baryons production in proton-proton collisions, and these measurements enable the determination of the total charm quark production cross-section with an unprecedented accuracy. as well as the charm fragmentation functions, which is what I'm showing here. So essentially the probabilities of the various charmed hadrons to be formed. And we found that these probabilities are not universals, as they were assumed so far. So they are not independent of the collision system. And actually, the observed charmed hadron distribution in proton-proton collision is very different from the previous measurements at electron-positron and electron-proton colliders. As you can see, for instance, the probability that the charmed barrier lambda C is formed is about 3 times larger in proton-proton collisions. Now, these results have stimulated an intense theoretical activity for their interpretation, mainly in terms of hadron formation mechanism that take into account the surrounding environment of strongly interacting particles. And well, they include explanations that contemplate the strong interaction charge connection across the whole set of particles produced in the collision, as well as the formation of hadrons by coalescence and various other approaches. Now, I'm showing here now a study. So the measurements I've shown before, they are instrumental then to the measurement of hadronization in heavy ion collisions. And I'm showing here a new ALICE preliminary measurement that uses machine learning techniques to discern the charm strange mesons, the sub-S, that originate directly from the hadronization of the charm quark from those that originate from the decays of beauty hadrons, so the non-prompt d sub-S mesons. And this, so the non-prompt d sub-S then compared to the previous measurement of non-prompt d0 mesons to gain sensitivity to the production of beauty strange mesons b sub-S. And these preliminary results show the probability of forming beauty strange mesons in lead-lead collisions tends to increase with respect to that of forming non-strange beauty mesons, although the data is not yet fully conclusive. And well, as you can see here, the measurement is described by a theoretical model that includes hadronization of beauty quarks by recombination with light quarks from the QGP. Now, these measurements will be much more precise in the upcoming run 3 of the LHC, and will provide more firm conclusion on this matter. Now, the last topic I would like to show is the use of the LHC as a general purpose QCD laboratory. In particular, one of the things we have been studying is the QCD interaction between hadrons, essentially any pair of stable and unstable hadrons. This is done using femtoscopic techniques. Here is the list of measurements that we have published on the topic in the past 2 years. And as an example, I'm showing here the results of precision measurement of the proton omega minus correlations, which was published on Nature at the end of last year. So where an accurate modeling of a small interparticle distance, which is of the order of 1 Fermi, together with the exact measurement of the correlation functions in the momentum phase space allows the determination of the short range of the nucleon-hyperon interaction. Now, by the way, this is, also the measurement of the proton sinus Xi minus, that they have also connections to astrophysics because they're relevant for the equation of states of neutron stars, which contain hyperon-rich matter. All right, so now let me move forward. Now, establishing the connections between this rich phenomenology of ultra-dense nuclear matter and its detailed understanding in terms of fundamental laws of the strong interaction physics, has motivated future improved measurements, for instance, of the soft, heavy flavor and electromagnetic radiation, calling for larger statistics and more precision on the measurement of hadronic and electromagnetic probes at low transverse momentum. And this has motivated a massive upgrade of the ALICE experimental apparatus, the preparation of which started 10 years ago, targeting an increase in statistics by 2 orders of magnitude for lead-lead collisions and 3 orders of magnitude in proton-lead and PP collisions. Of course, these are very large factors, and they're really going to help our physics programs a lot as far as rare probes and a variety of other observables are concerned. Now, the key items of this upgrade are illustrated here. Now, I do not have the time to discuss any of this in detail, but I would just like to show the new inner tracking system, which is a project to which well, the St. Petersburg State University has given very large contributions. So this is a new silicon tracker based on novel technology, ultra lightweight, using monolithic active pixel sensors with a very innovative carbon fiber mechanical support structure developed by the group of St. Petersburg, and also very novel cooling concept. Now, this detector is one of the pillars of this upgrade, and was successfully installed in May this year. I will just flash very quickly a few pictures which marked the milestones of the installation of the upgrades, the installation of the TPC, which has been largely upgraded in August last year, the installation of the mini frame in November, December. Now the installation of the new MFT with the fit detector, which are 2 other projects with large Russian contributions in December last year with let's say just the week before Christmas. And then this year, at the beginning of the year, the installation of a completely new computer farm for the online real-time data processing and event reconstruction, and the installation of the ITS in May this year, the installation of the completion of the installation of the FIT. And this is, again, a detector with a large contribution from Russia, and also the completion of the upgrade of the muon spectrometer, which also has several contributions from Russia. And so, we have now closed the magnet doors, which somehow marks the end of our successful upgrade plans. And we are now in the phase of global commissioning. So global commissioning started since mid of July with the integration of all systems, calibration of the various detector, and also detector alignment. Now, due to the COVID, we are also had to adopt a different way of operating our experiment, with essentially part of the shift crew on site at CERN, and part being remote in the so-called remote operation sites. But this is for now for the upcoming round 3. The things do not just stop there. For LS3 in 2025-2026, we have another exciting update of the ITS in preparation, which is going to involve the replacement of only the inner 3 layers of the ITS, which essentially are truly cylindrical silicon maps layers based on a novel technology with a much better performance. And in addition to that, we have also plans for a forward calorimeter for CAL, which is going to be able to perform the measurement of isolated photons at forward rapidities. But especially we have a very ambitious plan for beyond Run 4, going towards the 2030s, far in the future. So we're preparing a letter of intent for a next generation dedicated heavy ion detector, ALICE-3, which would buy us another factor 10 in terms of luminosity, with based on a ultra thin tracker, but also strong particle identification capabilities with time of flight, reach detectors, electromagnetic calorimeter, and immune identifier detector, covering a very large rapidity range. So this will give us ultimate performance on the measurement of electromagnetic and hadronic probes of the QGP to address a variety of physics themes. So the mechanism of hadron formation in the QGP transport properties, but also QGP electrical conductivity, the thermal radiation, access to the pre-hydrodynamization phase, current symmetry restoration, and much more. Now, the initiative which was presented at the in Granada at the European Strategy for Particle Physics update has received positive feedback, and we are now preparing a letter of intent, as I said, which will be discussed with the CERN scientific committees, the LXXI, in the fall. So we are much looking forward to have also this happen in a bit distant future. And with this, I would like to conclude. We collected a wealth of new results from Run 2 data analysis, but now we have the full Run 2 data analysis, which have offered a very offer insight into the QGP properties, but also allowed us to cover a broad program of high-density QCD studies. Now we have just completed the phase 1 upgrade of the ALICE detector in view of Run 3 and Run 4, which will enable a 100-fold increase of statistics and enhancement of vertexing and tracking capabilities at low transverse momentum. And this will be really fundamental to gain better insight into the QGP microscopic properties and dynamics, but also to understand better the heavy ion-like phenomena observed in small systems. And then I've shown that we have plans for continuing the heavy ion physics at the LHC with a dedicated next generation detector for beyond Run 4. And with that, I would like to thank you for your attention.
Okay, thank you very much, Luciana, for the nice presentation, for the warmest words for our conference. And now we have a time for questions. And maybe first one will be from my side. And could you please tell a few words about Run 5 in the technical context? For example, as I know, we have to remove TPC, for example, and use only silicon detectors. And it's very interesting for our audience, I think.
Yes, indeed. I mean, the time projection chamber is a wonderful detector because it provides a tracking, a continuous tracking in a very high particle multiplicity environment. And actually, I have to say that the performance of the time projection chamber has been spectacular, also at the particle rates that would have been considered totally impossible 20 years ago. with a very, very high occupancy, up to 50% in the innermost regions. Moreover, it also provides a particle identification. So it's a really wonderful detector. But it is clear that we are at the limit of what it can be done. Already in run 3 and run 4, as I said, the particle loads on the TPC will be such that the distortions will be very large. And so we have to go for very complex strategies to correct for the distortions due to the space charge. But even independent of the distortions, as I said, the occupancy is already reaching very, very high values. And so if we want to go to larger statistics, which is what is needed to measure certain probes, for instance, one of the goals will be to measure multiple hadrons like the omega CC, omega CCC. This really calls for very, very large statistics, but also other multi-differential measurements requires to accumulate large statistics. And so somehow we have to go beyond the TPC, which is by nature as a low detector, due to its projective nature of a very large drift lengths. And so the idea is to use silicon detectors, leveraging on the experience and technology that we developed for the inner tracking system, namely monolithic active pixel sensors. That will actually improve the tracking performance with a more compact detector, but of course it has to be complemented then with very powerful rich detectors in order to keep our particle identification capabilities.
Okay, thank you, Luciana. And colleagues, please raise your hand, and if you want, you can ask.
Can I ask a question, please?
Yes, Victor.
So, Luciana, you mentioned a 100-fold increase in the data sample in run 3 and 4, but it also means that the beam rate collisions will raise. What is the expected ITS performance for beam pileup? Because I would expect it become significant at this rates.
Indeed, the actual increase of the beam luminosity will be more like a factor of, well, depends on what we take as a reference. If I would take the average luminosity in run 2, would be a factor 10, okay, let's say order 10. Essentially going from 5 kilohertz interaction rate for lead-to-lead collisions to 50 kilohertz interaction rate. Now, when I'm referred to an increase of 2 orders of magnitude for in statistics, I'm referring to the fact that in run 1 and run 2, of course, we have been inspecting this luminosity with triggers, okay? And the actual capabilities of recording the minimum bias events was limited to a kilohertz, or actually even less, okay? So I've been running for a long time with a limitation to 500 hertz, and then only towards the end, we've been running at the kilohertz. So while in run 3 and run 4, we will be able to read out continuously and record all events. So we will have a factor 50 to 100 larger minimum bias events. And now most of the observables on which will be the focus, the scientific focus for run 3 and run 4 is actually our observables on which we cannot trigger, okay? So if, for instance, take most of the open heavy flavor, there is so much charm produced at the LXXI energies that essentially you would trigger on every event. So conventional hardware trigger techniques are not really applicable. So, but this is just an example, okay? So therefore, for most observables, most of our program, run 3 and run 4, this is effectively an increase of a factor 100. And now to come to your very specific point, what is the pileup? Well, we have, let's say, TPC with 100 microsecond drift length, drift time, so at 50 kilohertz. So this means an average pileup of 5 minimum bias lead collisions in the time projection chamber.
Okay, colleagues, please, more questions? Okay, if no, we thank again Luciana for the nice presentation, for the participation in our conference, for warm words, and thank you, Luciana, again.
Thank you very much, Vladimir. Thank you, everyone.
Good. And now I'm inviting also our best colleague and our friend from Gatchina, from Kurchatov Institute, from Petersburg Nuclear Physics Institute. It's a scientific director of Petersburg Nuclear Physics Institute. It's Vladimir Vladimirovich Voronin.
Yeah.
Yes.
Do you hear me?
Yeah. Very well. Yes. Okay.
Can start demonstration of my talk.
Okay, now it's okay.
Okay, dear colleagues, I'd like to see all of you. Thank the organizer of this nice meeting for this. Thank you for invitation to make this presentation here. First of all, I'd like to mention you that this year we celebrate the half of century of our institute. I mean, the independent legal, then our institute becomes the independent legal entity. Also, I'd like to mention that all history of our institute is slightly longer, because the institute was organized about 65 years ago, but initially it was as a department of the YOF Physical Technical Institute, and first 15 years it was the department of the YOF Physical Technical Institute, and only at 71, as it's shown here, in July of 71, it becomes an independent institute. And therefore, now we have 75 years of all history of our institute and half of century of history of our institute as an independent institute. And during this time, institute becomes the very famous and well-known in the world institute in the different large of scientific research, from the particles and the nuclear physics to the biology and the biophysics, molecular biology, and some applications, different type of applications. And now I hope that our institute is coming to the new stage, to the new era in our history, because just now in our institute, the one of the most powerful research reactor, which is intended to be the one of the most powerful neutron source in the world, are under commissioning. And I hope that this commissioning of this reactor give us a new pulse to the new science, to new research, because it opens unique possibility of scientific research due to their high flux and some extra experimental equipment which are under construction now also. So you can see, first of all, the photos of this complex, reactor peak complex. All buildings are ready, but not all equipment which should be installed inside these buildings are already commissioned, and now we are in process of the commissioning of the reactor itself and some extra equipment which is necessary to carry out the neutron scattering experiment. Because to make the neutron scattering experiment, we need not only the high flux research reactor with the maximum fluxes neutron inside the reactor, but also we need to prepare the neutron with a specific energy which we need for the experiment. We need some extra neutron sources, secondary neutron sources, which allow to prepare the neutron with a different energy spectrum. It's schematically shown here. The neutrons which we need for the experiment, not only thermal neutrons which appear in the reactors, which is shown here by green line. Also, we need cold neutrons. So these to prepare such a neutron, we need the moderator with a less temperature. Now we are going to use temperature of deuterium. Deuterium with a temperature about 20 Kelvin, and also we need not only thermal neutron and cold, but also hot neutrons with the energy about few times more than thermal. So we are going to prepare such a type of the source also. So we need high flux inside the reactor. We need specified system of neutron thermalization to prepare an energy spectrum which we need. Also, we have to transport these neutrons flux to the experimental station, and for this aim we will use some system of neutron gate system which transport neutron without serious losses on the distance about 100 meters to the hole of neutron gate hole. And also we need neutron scattering experimental station, which should be used for specified experimentals which we are going to use. To make the most highest flux of the neutrons inside the reactor organized as a water-water reactor with coolant by light waters and reflectors by heavy waters. And to obtain the maximum neutron flux, we need to increase the heat release per one volume unit. I mean that we have to decrease the volume of the reactor core with keeping some more or less power. So the reactor peak has power about 100 megawatt, and the volume of the reactor's core is only about 50 liters. It means then specified heat release is about 2 megawatt per liter, and this value is the maxima for the apparatus of such types. And this value limits the neutron flux, because the appear of one neutron coincide with a rising 200 megawatt of power. Therefore, this value 2 megawatt per liter limits the neutron flux which can be available, which can be reached for the apparatus of such type, and therefore the neutron flux in our reactor, in the moderator, is maximum for such types of machine, and are lying on the level about 1.3 on 10 to 15 neutron per square centimeter per second. I mean the flux of the thermal neutron already after thermalization. There is some very rare unique trap for neutron trap, neutron maybe beam, but some for some radiation. In the center of the reactor core, we have some channel, and the flux inside this experimental channel is a few times more, and this value is absolutely record for the reactors. It is 5 on 10 to 15 neutron per square centimeter per second, and this flux can be used for some irradiation and so on. Of course, not for extract this neutron to the experimental station outside the reactor. We expect the operation cycle of this machine about 30 days, about 25 days of operation and 5 days for reloading on fuel and some technical technicians process. To extract neutrons from the moderator, there are a lot of different channels. We have 6 vertical channels, 6 inclined channel, 1 central channel, and 10 horizontal channel, which is intended to extract the neutron to the experimental stations. You can see the construction of this experimental channel, this moderator with a lot of channel to extract neutron from the moderator. As already told, as already mentioned, there will be placed the cold neutron beam, which is cold neutron source, which is shown here the channel number 3. Also, hot neutron source will be on channel number 8, and therefore all green parts, the moderator, is the source of the neutron, the thermal neutron. If we compare the parameter of this machine with the existing experimental, with the existing reactor, with existing neutron source, one can see that the parameter of this machine is really at the on the best level, because the most close to our machine is the apparatus of high flux reactor in Grenoble, France, with the power about 58 megawatts and the flux about 1.5 on 10 to 15, which is about the same as a moderator in our machine, and the possibility to put about 40 instruments at the same time. It's about the same as we expect in our apparatus. But if we will see the situation with the current availability of the neutron beam, neutron experiment on the right plot, you will see that during the next few years, next maybe 10 years, the situation will be quite dramatical. This is a slide from the report of Colin Carlisle in the conference. You can see that after shutdown of the LLB reactor in Saclay in France, and after the shutdowning of the reactor ILL in Grenoble in France, in the next, I don't know how long time it will be still working, but I think that during the next 5 years it will be shut down, and after that the availability of the neutron beams, the possibility to prepare the neutron experiment at Europe, decreased dramatically. About 2 times less availability of the instrument of the neutron beams becomes less in comparison with the best days in 18 years. So even commissioning the new source, which is under construction in Europe, which is shown here by orange. It is ESS, European Spallation Source in Lund, Sweden. Even commissioning of this apparatus not compensate with dramatical decrease of the availability of the neutron beams in Europe. Therefore, reactor peak is very interested for the international cooperation, and all European, at least scientific neutron community, are looking for us with a high interest. And how we will work with how it will be commissioning, how it will be successful. So. And really, we are going to prepare the International Center for Neutron Research on the base of the reactor peak, and therefore this process is already started in some direction, because already first experimental station, which was commissioned at the end of last year, already was made with international contribution. Also, there is some program, Kremlin Plus, so-called Kremlin Plus. It's connection Russian and European mega science for large-scale research infrastructure, abbreviation Kremlin. The goal of these is some work at package 4, which is devoted to the scientific cooperation around the peak research reactor in the field of neutron source and neutron research. Also, the construction of our neutron gate system, which is shown here schematically, allows to put some extra experimental equipment which can be constructed at the framework of international cooperation. Not all beam positions are occupied by instruments of national instrumentation program. And also some process with Belarus as most close for us international country, for foreign country. The agreement on Belarus joining to International Center of Neutron Research has been negotiated now. So this process is already started also. And now let's consider what is where we are now with the reactor peak commissioning and our plan for the nearest future. This year we start the new regime, start a new etap, new phase of the reactor peak commissioning, the phase of call it 10 megawatts, which is called as energetic regime. And this process was started by our president, Vladimir Putin, online, of course, not direct. He was not visit our, but nevertheless, online he make some start of this process, 8th February this year. And now we have the approval of our state regulator Rostechnadzor for this regime, and we are going to reach these megawatts in the nearest, I hope that the nearest month. Schematically, the broad map of the reactor peak commissioning with the increasing of their power shown here. The first step about 100 kilowatt was reached at the end of 18, and now we are working also at this power about 100 megawatt, and as already mentioned, and at the middle of the next month, at the middle of October, we expect possibility to obtain this 10 megawatts or a few megawatts at least energetic power of the reactor peak. After that, there will be some shutdown about 1.5 years. Because we need to change the type of the fuel element, because now we have only one complex of fuel element for this first stage, and we need to construct to build, to prepare the another type of fuel element the next stage, full stage 100 megawatt will be started this and will be worked at this new type of the fuel element, which is expected to start it at the end of 22. And during a year, maybe, or maybe slightly more, but nevertheless, after starting, I think that the 100 megawatt can be achieved, can be reached during a year, and somewhere at 24th, we expect it to have about project power, about 100 megawatts. And also in parallel with the reactor peak commissioning, the extra equipment which is necessary for the neutron scattering experiment, also under construction and commissioning. The first 5 experimental station was commissioning at the end of last year. These stations was devoted to the experiment in the field of condensed matter. I'll show you later how it looks. And now the main program for the construction of the 20 full-scale experimental station is already started. So in parallel with the reactor peak commissioning, we construct all extra equipment which is necessary for the experiment. I mean, experimental station, secondary neutron sources, neutron gate system, and so on. The first 5 days stations, which was commissioned at the end of last year, shown here. It's 5 experimental stations which is placed around the reactor. There is reactor core at the center of this circle. So around this, at the whole of experimental channel, there was placed 5 experimental stations. Photo of these stations shown here. They are working, but of course for the power 100 kilowatts, it is not very serious for some interesting scientific experiment. We make only some tests and some alignment and some demonstration experiments, but nevertheless it is also very important because it is first experiments which was done on the reactor peak. And now these 5 experimental stations realize some base experimental technique for the condensed matter. I mean that two of these experimental station is reflectometers to study the reflection from the surface of neutrons, two diffractometers to study the crystal structure and variation of this crystal structure, one monocrystal diffractometer and one texture diffractometer, and one test neutron spectrometer to measure neutron spectrum and what beam we have, what neutron we have in our reactors. The main part of the instrumentation program realized at the framework of the national program of synchrotron and neutron research, which was started at 19. At the September of last year, September of 20, we obtained the positive decision of the state expertise and possibility to start the process of the instrument construction. And also now the all construction of the instruments are separate and in three stage. The first stage was started at the end of at the beginning of this year. The second stage was started in June of this year, and the third stage will be started at the beginning of the next year. All this process shown here in this roadmap. At the framework of this instrumentation program, they have to build 20 instruments. 20, yes. 20 instruments, numeration is wrong, sorry, but nevertheless, all number is 20. It's real. 20 instruments, as already mentioned, is separated in three phases: first phase, second, and the third phase. Also, it is in experimental stations, but also we need this few neutron sources. It's shown here: two cold neutron sources, hot neutron source, and ultra cold neutron source, which is under construction. Also now it started. This process is also started on neutron gate system, and the instruments which is colored by green it's devoted to the nuclear and particle physics. So at the framework of this program, we have to build 7 instruments for the nuclear and particle physics, and I show you discuss it slightly less later. Sorry. Okay. And what we obtain after the realization of this program for the particle nuclear physics, very brief review of the instruments, these 7 instruments which will be constructed as the framework of this instrumentation program. All devices is shown here: 7 instruments, 2 stations on cold neutrons, 1 neutrino facility, 3 stations for neutron spectroscopy and applications, 1 for fission physics, and ultra cold neutron source. Ultra cold neutron source, also for nuclear and particle physics. The most powerful, most interesting, I think it is a ultra cold neutron source, because they expect to obtain the density of the ultra cold neutron source at this machine, which will be placed at the channel number 4 of the reactor peak. This picture, this is moderator, this is reactor core, this is experimental channel number 4, and here will be placed the ultra cold neutron source, which is based on the direct conversion of cold neutron to the ultra cold neutrons using superfluid helium-4 at the temperature about 1 Kelvin. It is very difficult technical task to put here about 35 liters of the superfluid helium at the temperature about 1 Kelvin close to the reactor because of heating, and it is irradiation heating, but nevertheless all calculations demonstrate that it will be possible. So, and we plan to obtain the density of the ultra cold neutrons in this source about 2 orders more than the so increasing of the density of this and ultra cold neutrons allow us to increase the sensitivity, sensitivity and accuracy of the main measurements which can be done with ultra cold neutrons. I mean the experiment in neutron, it measures the neutron electric dipole moment can be improved at least on 1 order. Also, we can improve about one order the accuracy to measure the Newton time of life, which is very important now because there is some differences in experimental results for different type of experiment to measure the neutron lifetime. And also the experiment of mirror neutron oscillation also can improve the accuracy about one order, because simple increasing the neutron flux, neutron density of the ultra cold neutrons. What is important that all these 4 instruments already exist, and now they're staying on the reactor ILL, on the already exists, already tested to work very long time. So we know what we can obtain using this experimental apparatus on our reactor after the commissioning of the new type of the ultra cold neutron source. Also, one experiment also connected to the study of the neutron properties, property of neutron decay. It's a neutron beta decay experiment which will be done on the cold neutron beam source. It's shown, can be returned here. Here one can see this apparatus also placed at the facility near the ultra cold neutrons, but nevertheless it works with this cold neutron, which is allowed to measure the correlation in the neutron beta decay. As you know, the neutron decay in the proton, electron, and antineutrino, and we can measure the correlation, angular correlation of this this process with accuracy about 10 to minus 3. That is about one order better than they ever now. So the next facility is the neutrino facility. Now there is some problem with the neutrino. There is some deficit of the reactor neutrino, as you know, and this deficit can be explained by the oscillation neutrino to some sterile state of the neutrino, some false type of the neutrino, and this oscillation can be on the very short range. Therefore, the reactor peak is very good for such type of experiment because of very compact reactor core, allowed to measure the short range oscillation of neutrino. And this facility will be organized also at the framework of this program on the reactor peak. The parameter of this apparatus is shown here, and I hope that it is allows to solve the problem of deficit of the reactor neutrino. Also, one experiment which will be done on the cold neutron beam. It is another type of the cold neutron EDM experiment to search the neutron EDM using the diffraction in the crystal without center of symmetry. The main advance of this experiment is the huge value of electric field which can affect the neutron in the non-centrosymmetric crystal. This value is about 10 to an 8, 10 to a 9 volt per centimeter. That is about 4 or 5 orders more than ultra cold neutron methods measure the neutron electric dipole moment. And this is absolutely different technique. Therefore, this experiment will be realized at the framework of our instrumentation program on the cold neutron beam at the neutron gate hole. Yeah. Some preliminary preparation of experiments shown here. We are going to use the crystal quartz, non-centrosymmetric crystal quartz. This quartz crystals is already tested and exists, and some preliminary test experiment was done at the ILL reactor PF1D beam a few years ago. Also very important and very powerful facility. It's facility IRINA for investigation of radioactive isotope with neutron. We are going to put on the flux about a few on 10 to 13 neutron per square centimeter per second. The target from the uranium to uranium 5, and see the project of the decay of this uranium under the thermal neutron. the yield of some isotopes, and this if we are going to use rather large target with a few grams of uranium-5 with a high enriched uranium-5, a few grams, and the large of the neutron flux allow us to obtain the yield of some isotopes a few orders more than they ever, and therefore we will be able online study the properties of the long life isotope enriched by neutron, and so forth. The program of this instrument is very powerful and very interesting. And also what is important, that this apparatus can be used for some application, because it will be able to produce the very clear isotopes for medicine, for instance, or for some other application, because we plan to use the unique technique for the laser isotope ionization, which was developed in our institute, which can separate different isotope ionization using laser system and laser resonance spectroscopy, and which allow to separate and to ionization of specific isotope, and therefore we can be obtain here already very clear isotopes beam, and which isotopes can be used not only for some fundamental physics, but also for some application medicine and so on. Also, we are going to construct so-called FISCA facility, fission correlation detectors, which will be placed at the neutron gate hole, also on the beam number 9. This FISCA facility will be able to study angular correlation as the ternary fission by cold neutron induced by cold polarized neutrons, and the studies well-known ROT3 effect and PNC effects. Study the angular correlation, gamma quantum neutron emission, and so on. We are going to construct two options of this isotope. One of these isotopes, two options of these detectors, two options of this machine. One is the detector of fission neutron detectors multiplicity, and the second multi-section detectors of fission neutron and gamma quantum. As I already mentioned, will be placed in the neutron gate hole and the channel number 8 also for fission. One instrument which will be devoted for the application, it is neutron instrumentational activation analysis. This installation will allow to determine the content of the isotopes and elements with a very high accuracy online with the measurement, because it will be placed, it's shown here, unfortunately, we can be able to use the long life nuclide, study long life nuclide, because they will be organized as a very fast delivery from the radiation point to the shown here, for instance, something like this, that can be placed very quickly to the detector. And also at the neutron gate hole of the inclined channel, where will be placed the neutron activation analysis experimental station, where will be constructed also the final instrument in my talk. It is instrument progress to study the nuclear structure using the study the neutron and gamma reactions in gamma coincidence. The scheme of this device is shown here. Some sample neutron beam and two high purified germanium detector, which is allowed to measure the gamma quantum, which emitted by the target after the capture the neutrons, and we will be able to study the neutron nucleus structure. So it is all what I want. What will be constructed at the framework of our instrumentation program. I'd like to come back to this roadmap and demonstrate you that some of this instrument is already started. I mean, the neutron activation analysis and neutrino facility is already started. Also, already construction of this instrument already started. Also, free instrument IRINA diffraction VDM and FISCA also started a few months ago, and 2 instruments will be started at the next year. And all this program have to be finished at the end of 24th. And I hope that this ambitious program will be realized, and somewhere at the end of 24th and 25 year, we obtain not only the reactors, commissioned reactors, but also the all instrument which allow us to measure not only the structure, material structure, I mean the condensed matter physics, and also the physics, to make the physics in the particle and nuclear physics. And so thank you very much. I hope that this program will be realized, and you'll see. Thanks.
Okay, thank you very much, Vladimir Vladimirovich. Very nice report, and we can see the big progress in the big reactor campaign, and in particular for neutron station. And from the also organizing committee and from our conference participants, please accept our congratulations on 50 anniversaries of Petersburg Nuclear Physics Institute, and please accept our greeting card. And in this context, I'm remembering one story when I was young and I worked in the WWRM reactor. My colleague told me about a story when this reactor was constructed. Professor Rusinov said, we have to obtain the first physical results, and we have to report these results in our spectroscopic conference. It was in, I think, 1960, a little bit. And yes, it was reported in our conference, physical results from that reactor. And Professor Rusinov said that we get the first neutron in Gatchina. And I think we will get a second one from the reactor peak, and you will report us in our conference about physical results from these investigations, and promise us.
Oh, yeah. Thank you, Vladimir, for your nice mention. Thank you very much.
Okay. And okay, thank you again. Maybe colleagues have a question, please. Okay. If not, thank you again, Vladimir. And now we are closing morning session, and we are going now for the coffee break. And how? We have only 5 minutes for the coffee break. Okay, we will start another session in 10:50. Yes. Okay, thank you.
Vladimir, could you please stop sharing your slides?
Yeah, sure. Victor, you want to try to upload your slide? Yeah.
That's the plan.
Yeah. Or you don't like our greeting card?
I like it quite a lot. Okay, so can you see my slides up?
Yes, yes, very well.
So-
Yeah,
so
it's a full screen, yes.
Okay,
It's
so
okay.
let's start in like 3 minutes.
Yeah.
На нашем родном выступать. Потому что я меняться на английском, я могу и так, но хочется все-таки как на своем уверении.
Конечно, да. Ну, пленарное состояние одно, а секция это другое.
Нет,
да.
я согласен, да.
Да, да. Секция.
Okay, dear colleagues, we are starting now the second half of our morning session, plenary session, and we'll have two big reports from Nika, from two big collaboration on Nika Collider. And for the first speaker, I'm inviting with great pleasure Viktor Ryabov. It's for the MPD, multipurpose detector collaboration. Victor, can you hear me?
Yes, I can. So thanks for the introduction. So in my talk, I will review the current status of the Nika accelerator complex, which is now under construction in Dubna, with emphasis on the progress of the MPD detector and its expected physical capabilities in the first years of operation. So the Nika is one of the mega science projects in Russia, which is expected soon to come into operation. And the main scientific purpose of the MPD detector is to search for novel phenomena in the baryon-rich region of the QCD phase diagram by colliding heavy nuclei in the energy range from 4 to 11 GeV. As you know, lots of results have been obtained in heavy collisions at different energies by experiments carried out at several facilities such as Bevovac, CS, AGS, SPS synchrotrons, RIC, and the LHC. and the corresponding event rates and the covered collision energies are illustrated in the plot on the right. The experimental program of the NICA is in the energy range, which is not yet fully explored. The rich structure of the QCD phase diagram is shown on the left, thanks to Luciano for the nice introduction. The solid and dashed lines indicate the critical lines of the first order and crossover transitions. The critical endpoint occurs where solid and dashed lines meet. And if the confinement and chiral symmetry restoration do not coincide at high baryon densities, there can be a critical point when between the hadronic and quark-gluon plasma transition lines, a third phase like quark-ionic matter or color superconductivity can be realized. It is expected that it is predicted that the highest baryon densities are achieved in the NICA energy range in heavy-ion collisions at NICA energies, which makes the MPD well suited for search of the critical point if it exists. In general, the MPD strategy consists of performing a high luminosity scan in energy and system size, looking for different signals expected to have a non-monotonic behavior. The scans are going to be performed using the same apparatus with all the advantages of collider experiments, such as large and uniform acceptance, absence of target parasitic effects. The fixed target experiments, on the other hand, have their own advantages, such as a high rate of interactions, easy access and upgrade capabilities, and better vertexing for heavy flavor studies. The schematic view of the NICA accelerator complex is presented in the slide. Beams from ion source are accelerated in booster and then injected in the nucleotron. Beams from the nucleotron can be extracted in the experimental hall of the fixed target BM10 experiment. The nucleotron beams can also be injected into the NICA collider. And there are two experiments, the NICA and the SPD. And the dates in this figure reflect the planned commissioning schedule. Another view of the NICA complex is shown in the next slide. The ion source and the linear accelerator inject beam in the booster, which has a length of 211 meters. It accelerates ion beams up to 600 MeV per nucleon. Then the ion stripping and injection to the nucleotron happen. And the nucleotron accelerate beams up to 4.5 GeV per nucleon and then injects beams to the NICA rings, which have a length of about 500 meters. The designed energy range of NICA collider is from 4 to 11 GeV, as I have mentioned, with a maximum luminosity of heavy ion beams of 10 to 27. It is expected that, well, it is known that not all critical elements of the accelerator complex will be ready for day one operation. In the first year, additional acceleration of the beams in the NICA collider is not foreseen. Therefore, the initial collision energy may vary from 7 to 9.46 GeV. And the collision energy of 9.2 GeV was preferred so that first results could be compared to those obtained at STAR at RIC collider with results taken at the same collision energy. The collider will be operated without electron cooling in the first year and with a reduced number of RFs, which will result in the reduced beam luminosity. And the goal for the first year is to have a luminosity of 10 to 25, which would correspond to a collision rate of about 100 Hertz or even less. The available nuclei are limited by the ion source, and we plan to start with bismuth collisions at 9.2 GeV in 2023. At this, delivering gold collisions at maximum energy of 11 GeV remains as one of the key goals of the NICA project. One of the important milestones became the commissioning of the booster. The booster superconducting magnets have been produced in Dubna and installed inside the old synchrotron iron yoke. And the pictures in the slide show the outer view of the accelerator, and the commissioning and the tests of the booster are ongoing right now. In the end of 2020, last year, the first technical run of booster took place. The accelerator was cooled down and injected with helium ions at the energy of 3.2 MeV per nucleon. The beam was successfully accelerated up to 100 MeV, while the design energy is 600 MeV. So the plot on the left shows that magnets are operational and provide the design magnetic field and ramp rate. The plots on the right show the acceleration, storage, and deceleration of the ejected beam. The lifetime of the beam corresponded to beam pipe pressure of 2-3 times 10 to minus 10 torr. Here is a simplified NICA schedule. So the main achievement for this year will be the full run of the booster and nucleatron with different beams. Construction of the NICA rings and transport lines should be finished next year. Meanwhile, construction of the MPD detector should be ongoing. In the end of 2023, we expect the first technical run of the NICA complex with bismuth-bismuth collisions at 9.2 GeV. The idea is to collect about 100 million good minimum bias events with the MPD detector to be used for detector alignment and calibrations, and hopefully for the first physics analysis. For 2024, the top priority is to deliver go-gold collisions at the maximum energy of 11 GeV to fulfill the program. And for 2025 and beyond, the priority will be to reach the maximum beam luminosity, and the beams and the energies will have to be decided based on the requests from physicists. The MPD International Cooperation has been established in 2018 to construct, commission, and first of all, operate the detector. And at the moment, it consists of specialists from JINR and 39 different institutions from 11 countries. And well, the MPD is open for new members, so if you are interested, consider to join. An artistic view of the MPD detector is shown in the slide. The MPD is designed as a 4-pi spectrometer capable of detecting charged hadrons, electrons, and photons in heavy-ion collisions, which are characterized by very high multiplicities. It will provide precise tracking and high-performance particle identification based on a large volume time projection chamber, time of flight measurements, and calorimetry. The detectors are placed inside of the superconducting solenoid with a field of half a Tesla. The fast-forward detectors and the hadronic calorimeters will solve for event triggering, event centrality, and reaction plane measurements at forward rapidity. Later, the detector will be upgraded to include the inner tracking system for heavy flare measurements and the forward spectrometers. Plots on the bottom give some feeling about the TPC momentum resolution capabilities of the TPC and TOF to identify charged particles, and energy resolution of the ECAL. All of this estimated for mean bias go-gold collisions at top energy of 11 GeV, of course, using RQMD as a event generator and full chain reconstruction. The MPD experimental hall is now available for detector activities, and in the plot on the left, you can see the full iron yoke assembled in the service position. One of the recent milestones became the installation of the superconducting coil in the magnet yoke, and the delicate procedure is illustrated in plots on the right. The next steps would be the cooling and tests of the coil with liquid nitrogen and then with helium, precise magnetic field measurements. And if everything is in accordance with the design parameters, then the installation of the support frame should follow, and the installation of different detector subsystems. All MPD subsystems and elements for phase 1 detector are either ready or in production. And this slide provides some very basic information. For more details, you can look at the site or in the backup slides. So as I mentioned before, the magnet is in advanced state. And after the magnet is tested and the magnetic field measurements are performed, the carbon fiber support frame will have to be installed inside the magnet. The support frame, we have to withstand the weight of all subsystems, including the electromagnetic calorimeter. And the producer of the frame assures that the frame sagitta will not exceed 5 millimeters at full load. The innermost detector in phase 1 is a time projection chamber, which is produced in Dubna. The TPC cylinders and the readout chambers have been fully produced. The electronics based on Sampa chips is in mass production. After the TPC goes the TOF subsystem, which consists of 280 MRPC chambers. About 40% of the chambers have been produced and packed in the slots in Dubna, which are now ready for installation, and mass production of the remaining parts is ongoing. All needed elements have been purchased. And the outermost subsystem is an electromagnetic calorimeter with projective geometry. The calorimeter is built of about 40,000 Shashlik type lead insulator towers. Towers are assembled in modules, 2 by 8 towers each, and then in baskets, which are then rolled in the support frame. 3 full sectors out of 25 in total have been produced, and additional 14 sectors are in production for stage 1. So most probably for phase 1, we won't have the full acceptance calorimeter ready. The physical program of the PND experiment is not unique. It has much in common with physical programs of other heavy ion experiments at different facilities. There are 5 working groups in the collaboration, which focus on the measurements of global observables, measurements of spectra of light flavor hadrons and hypernuclei, measurements of correlations, flow and fluctuations, measurements of electromagnetic probes, such as photons and dielectrons, and measurements of heavy flare production, which is probably not a realistic task for the first years of operation. In the next slides, I will present some selected results of physics feasibility studies that demonstrate the MPD capabilities and sensitivity to different observables. The studies were performed within the framework of MPD root and include the full chain of the detector simulation and event reconstruction based on our current best knowledge of the performance of different subsystems. Centrality is a key parameter for defining the collision system size and relativistic heavy ion collisions. In the MPD experiment, 2 procedures are considered for the centrality determination. And the first one is based on the charged particle multiplicity information provided by the TPC. And the second one uses the energy of spectator fragments measured at forward rapidity. So the plot on the left shows the multiplicity distribution measured for charged tracks at mid-rapidity in the TPC in case of gold collisions at 7.7 GeV simulated by RQMD wind generator. To reproduce the experimental multiplicity distribution, a Monte Carlo Glauber model coupled with a model for particle production based on a negative binomial distribution, and the gamma fit method were used. After the fitting procedure, the models are used to estimate the initial geometry of the centrality classes, and mean values of the RMS of the impact parameter distributions are shown on the right as a function of centrality, and the reconstruction quality is demonstrated in 2 panels on the bottom. And I can mention that other wind generators such as PHSD and SMASH and other collision energies we also tried, and they produce comparable results. FHCAL provides the wind centrality by measuring the energy deposition and space distribution of spectators. Unfortunately, most of the bound fragments escape through the beam hole in the FHCAL center. Therefore, the dependence of energy deposition in the FHCAL on the impact parameter is not monotonic. And to resolve this ambiguity, the 3-dimensional energy distribution in the FHCAL is fitted by a cone. And this fit provides additional parameters such as the height of the cone, its radius, and volume. And in the plot on the left, the correlation between the height of the cone and the energy deposition is shown. and it helps to distinguish the central and peripheral events, even if they have very similar total energy depositions in the calorimeter. The distribution is divided into 10 intervals, each containing 10% of the events, and the distribution of the impact parameter for each interval is then fitted by a Gaussian, as shown on the bottom, and a plot in the middle shows the central dependence of the width of the Gaussian fits for two event generators. High segmentation of the FHCal also provides the means to estimate the event reaction plane with the resolution shown in the rightmost plot. The structure of the QCD phase diagram may be tested by measuring the abundances of different hadrons, and since MPD has quite good particle identification capabilities and within a large and uniform acceptance, this is a task 1 for the MPD, and all this helps to perform systematic studies of particle yields and ratios as a function of collision energy, centrality, and different kinematic variables. And results of such scans eventually will be compared to model calculations and to the available worldwide data. Of course, one of the first planned measurements is the production of charged pions and canes near the maximum in the strangest to entropy ratio. And to estimate the sensitivity of the MPD detector to these measurements, a detailed Monte Carlo study has been performed with a PhD event generator, which implements both deconfinement and chiral symmetry restoration effects. And 3 plots on the left show the available phase space for the measurements in terms of rapidity and transverse momentum. The MPD samples about 70% of the total charge hadron production, and unmeasured hadron yields at low PT or at large values of rapidity can be extracted from the extrapolation of the measured spectra using some physics-motivated functions. The excitation function of the mid-rapidity k plus 2 pi ratio is shown on the right, with the chiral symmetry restoration switched on and off. The results of the performance study indicate that the experimental setup can allow us to measure the hadron yield ratios with small uncertainty. In this particular case, the difference between the reconstructed k2 pi ratio and the generated one is as low as about 3%. The MPD detector can reconstruct weakly decaying hyperons using secondary vertex reconstruction and topology cuts. The charged daughters can also be identified in the TPC and TOF if matched. And in the slide, you can see examples of the invariant mass distributions accumulated for pairs of daughters, where you can see peaks from decays of lambda, sigma star, and capital omega baryons reconstructed with rather large signal to background ratios. The gold events at 11 GeV simulated by PhD were used as input for the studies. The estimated yields of hyperons for about 500 million sampled events are listed in the table on the bottom, and the yields are high enough to allow for multi-differential hyperon studies with adequate statistics. The MPD has sufficient coverage to study both the rapidity and the transverse momentum distributions of hyperons and antiparticles. And as an example in the slide, you can see fully reconstructed transverse momentum spectra for lambda and psi baryons in most central on the left and peripheral in the middle gold collisions. The spectra were obtained by correcting the raw yields extracted from the invariant mass distributions shown in the previous slide by the reconstruction efficiencies shown on the right. And the figures show the reconstructed yields with blue markers and the generated spectra with black histograms, and the reconstructed and the generated yields match within just a few %. Short-lived hadronic resonances such as rho, k star, phi, sigma star, lambda star, psi star, and others carry information about the hadron chemistry and strangeness production, about the reaction dynamics, about density and lifetime of the hadronic phase. The heavy ion collisions ethnic energies are characterized by the final state charged particle multiplicities, at which the production of resonances measured at recent LHC energies has been significantly modified. The study of the resonance properties ethnic energies using different event generators also confirmed the modifications, and all this makes study of these particles interesting. Plots in the slide show the invariant mass distributions accumulated for different hadronic decays of resonances in Gold collisions at 11 GeV generated by RQMD. The distributions are shown after subtraction of the mixed event background, so don't be surprised by good signal to background ratios. With identification of hadrons in the TPC TOF and TOF, the MPD can reconstruct even the multi-stage decays of resonances with weakly decaying daughters. The next slide shows examples of the fully corrected PT spectra reconstructed for resonances in Gold collisions at 4, 7.7, and 11 GeV with markers of different colors. The truly generated spectra are shown with solid lines of the same colors, and the reconstructed spectra match the generated ones within uncertainties, confirming the detector capabilities. And first measurements for resonances will be possible with about 10 million sampled Gold events. And for most of the cases, the measurements will be possible starting from zero transverse momenta, which is very important for their physics. The anisotropic collective flow is one is of interest because it is sensitive to the transport properties of the medium produced, to the equation of state, to the speed of sound, to specific shear viscosity. The first order phase transition between the hadronic and the QGP phases is expected to be characterized by softening of the equation of state. The elliptic flow V2 is known to be the most extensively studied observable. However, high statistics, differential measurements of V2, the function of centrality, PT, and rapidity for different particle species are mostly available for 2 beam energy regions above 7.7 GeV at RIC and the LHC and below 2 GeV at CIS. And the MPD plans to produce high statistics differential measurements of VN, different orders of flow at intermediate energies. For example, in the slide, one can see in comparison of the reconstructed and generated V2 coefficients evaluated for pions and protons in Gold collisions at 7.7 GeV, simulated by RQMD, and passed through the whole reconstruction chain. The flow was measured using different methods, and all of them resulted in V2 values very similar to generated ones. The MPD also has the ability to measure flow for V0s, and here in the slide, you can see examples of V1 and V2 measurements for K-shot and lambda using the invariant mass fit method. The study was performed for Gold collisions at 11 GeV. The reconstructed VN signals, V1 and V2 signals, are in agreement with the generated signals, and similar analysis are, of course, foreseen for other hyperons and resonances. It is a very wide field of study. The MPD has good capabilities to study the production of neutral mesons decaying in channels with photons in the final state. The neutral meson measurements are complementary to identified charge hadron measurements by extending the kinematical ranges and expanding the variety of the measured particles to eta and omega mesons and probably to heavier hadrons in the future. For neutral meson measurements, the MPD can utilize the large acceptance calorimeter. An alternative is to reconstruct conversion pairs using the tracking system and electron identification. And in the slide, you can see examples of the invariant mass distributions reconstructed at low momentum for photon pairs in the ECAL on the left, and with photon conversion in the middle. The conversion method has the advantage of much higher signal to background ratio and better energy resolution. Similar was observed in other experiments. And for example, comparison of the widths of P0 and its meson peaks reconstructed in the ECAL and with the conversion method is shown on the right. And one can observe much narrower peaks reconstructed with the photon conversion method. And finally, 3 plots on the bottom compare the reconstructed P0 and its meson spectra with the generated ones. The spectra are consistent with an uncertainties, telling us that the measurements of P0 and its mesons will be possible in the first years of running. Measurements of photons, including thermal photons, is one of the topics of high interest. The thermal photons radiated by the produced medium carry information about the effective temperature and development of the collectivity. And we are interested to measure the yields and the flow of these particles, and it is a very, very challenging task for the MPD. There are not so many predictions for direct photon yields available on the market. Our model estimations and the empirical scaling based on the findings of the Phoenix collaboration predict R gamma values to be on the level of 5–10% at top Nika energies. The Phoenix collaboration developed experimental methods to measure R gamma values as low as 5%, and we now try to adopt these methods for the needs of the MPD detector. For photon reconstruction, the MPD has a colorimeter, which becomes most effective at high energy, and the conversion method, which provides about 1.5% reconstruction efficiency of photons, with very high purity, higher than 95%, even in more central gold-gold collisions. The electron spectra are sensitive probes of the deconfinement and the chiral symmetry restoration. Similar to photons, they are penetrative probes carrying information about the medium at the time of production. The dilepton yields in the intermediate mass region from 1 to 3 GeV over C square is most appropriate for observation of the thermal radiation from the QGP. The inverse slope parameter of the invariant mass spectra in this mass range is closely related to the initial temperature of the fireball. The dilepton yield in the low mass region below 1 GeV has been found enhanced in all heavy ion experiments, in all heavy ion collisions at all energies. The measurements at RIC, SPS, and HADES are consistent with the domination of thermal radiation from the hadron gas. Restoration of chiral symmetry manifests itself in a broadening of the rho meson spectral function. What's important is that dilepton excess in this mass region is proportional to the fireball lifetime, and the change of this proportionality at Nika energies, if found, of course, can signal critical phenomena and the onset of a first-order phase transition. The MPD is well suited for the study of electron pairs, covering the entire invariant mass range of interest, from low masses to J psi. Electrons can be identified in a large acceptance using TPC, TOF, and the ECAL, and plots in the slide demonstrate the reconstruction efficiency for electron tracks with different selections and the achieved electron purity, which can be quite high when all 3 detectors are used simultaneously. The plot on the bottom shows an example of the invariant mass distribution reconstructed for gold-gold collisions at 11 GeV. The combinatorial background is quite high, it's very high, and we continue to work on the methods to suppress it. However, the mass integrated signal to background ratio 5–10% achieved so far looks quite promising, well, and it doesn't prevent the success of the physical program. So, and here is the summary. The MPD experiment will be the primary detector at Nika accelerator complex in Dubna. The complex is in construction phase with many important milestones achieved. Commissioning of the collider and the MPD is expected to happen in the end of 2023 with bismuth beams. We hope for bismuth collisions at 9.2 GeV. And now the collaboration carries out extensive preparations of the MPD hardware, computing infrastructure, and the analysis tools for the first beams. Thanks for your attention.
Okay, thank you very much, Victor, for the nice presentation, and in particular in the physics aspects, because it's real important to know for which reasons we need such a mega facilities for niche physical reasons. And please, colleagues, questions for Victor? Colleagues, feel free to ask our speaker. It's an online conference and we not punish you. Okay, maybe I have a short question about second stage of MPD experiment, because we are working here in St. Petersburg University for vertex detector for intertaking system with our colleagues, and maybe, yes, a few words about some physical tasks and also.
Well, as you understand, all attention and all efforts are now to start the detector in stage 1, because it is a very challenging task. We also should keep in mind the pandemic situation, which is prone to delays and well, problems because of lack of contacts face to face. Although situation becomes better, it's not perfect. So for the upgrade, the first important thing which is expected to come is an internal tracker, silicon tracker for heavy flare measurements. It will come for sure, because it is already well, in deep research and in prototype test stage. So it will come. I cannot tell you at what year, because, but we expect that it will come in a few years after the start of the phase 1 program. What's for forward spectrometer situation is more complicated, because first we need to understand the physics, which can potentially be studied with these forward spectrometers. Also, we should better understand the background situation, because on the flanges of the TPC, we have quite massive metal structures for cooling to support electronics and so on. And the situation with background should be better understood. And if we have some clear physics cases for the forward spectrometers, and we understand that these cases can be studied in the current background situation, we will have to design the forward detectors and then build the forward spectrometers. As far as I understand the situation with funds and with the exact construction of the forward spectrometers, all this is not very clear. In case the physics case is clear, but the background situation is not acceptable, we will have to rethink the construction of the flanges of the TPC. So there is a flexibility what's going to happen with forward spectrometers. They are in principle foreseen, but there is no strict schedule, or there is not even a strict physical program for the forward spectrometers in the moment. But the ITS, it is important, and it will be installed. We probably don't need it in the first years, while the beam luminosity is not as high. But once the luminosity approaches the design parameters, we will need it to study the heavy flare. It will also help to study hypernuclei decays. I don't know how much it will comply with dielectron measurements, because it will be a significant source of conversion. But on the other hand, it will help to suppress conversion in the TPC inner vessels. So some kind of, it might be a good compromise actually, but this question I think deserves a separate study.
Okay, thank you. Dear colleagues, more questions? Okay, if not, we are thinking again, Victor,
Thanks
for the nice presentation. And now we are switching for the next speaker. It's another big collaboration from Nika Collider. It's a spin physics detector collaboration. Another Victor Kim, will tell us about progress of this spin physics detector. Please, Victor. Can you hear me?
Victor, you are muted.
Okay. Victor, we don't hear you.
Can you hear me now?
Yes, now it's very well.
I'm sorry.
Yes, we can see your slides. And could you please make a full screen?
Is it okay now?
Yeah, very nice. Yes, good.
Okay. First of all, I would like to thank the organizers for so good organization and great efforts to keep continuing second year in a row. And this legendary conference, actually, it's a great honor and pleasure to give a talk in this meeting. So I will talk about the physics with SPD experiment at Nika Collider, which is complementary to the discussed earlier MPD detector. So SPD, it is spin physics detector, a universal particle physics facility at Nika Collider. And main SPD goal is understanding of strong interaction using both polarized and unpolarized PP and deuteron-deuteron collisions at square root of energy up to 27 GeV at high luminosity. To reach this goal, it will be studied 3-dimensional quark-gluon structure of proton and deuteron with emphasis on gluon PDF, particle parton distribution function, and transverse momentum distributions at high values of X. In addition, it will be carried out a comprehensive program at the initial period of data taking for a broad range of particle and nuclear physics. So this is general layout of Nika. So you can see the SPD detector position. So SPD will work at very high luminosity, up to design luminosity up to 10 to 32, and energies in unpolarized and polarized case with different polarizations, longitudinal, transversal, for proton collisions, and for deuteron-deuteron, and possibly for deuteron-proton and light nuclei. So this is picture from May of this year. Now is less sunny and also more progress. And one of the features of this detector, it's very quick detector, and no hardware trigger is designed as the SPD detector to avoid a possible bias, but it will be special online filter. So the data rate flow actually is comparable with such detectors like CMS and Atlas at Large Hadron Collider, but of course the event size is smaller. So SPD setup is a medium scale detector in size, but a rather large scale in the data rate. So how it looks SPD project in the world landscape of polarized physics. First of all, we have a different facilities for polarized PP collisions. It's right plot above. So SPD can scan energy from few GeVs to 27 GeV square root of S. So it covers just between earlier studies at Saclay and also Protvino, 2 Phoenix and Star at RIC, BNL. But of course, each range has own interesting features. So, for example, below on the left plot, we can see the different features of the accelerators. Also, plant accelerators like electron-ion collider, and after it, LHC fixed target possible project and LHC spin. So you can see that, for example, for polarized deuteron-deuteron mode, SPD will be unique detector to study this interesting mode. Why it's interesting, I will tell you a bit later. So brief SPD project timeline. So idea of SPD project was included to unique activities at JNR in 2007 as idea. In 2014, SPD letter of intent was approved by JNR Physics Advisory Committee. In 2016 and 2018, it were held 2 SPD-oriented physics workshops in Prague. And in 2019, SPD project was approved by JNR PSC up to 2022, then it will be reevaluated. And in 2019, there was first SPD protocol collaboration meeting. Last year, it was completed SPD conceptual design report, and also it was prepared. It were prepared 2 SPD physics papers. One of them already published. Another will appear soon. I will give you reference also later. So this July, SPD collaboration was established, and also from the beginning of this year, SPD technical design report also started. So it is expected then in 2025 plus somewhere, depending on these uncertainties, it will be start of SPD operation. So as I said, SPD collaboration was established in July of this year. So currently in this project involved 33 laboratories and individual contributors from 14 countries, around 300 participants at the moment. So it's also growing. So people interested in can ask to join our mutual efforts. I will tell you a few physics highlights. As I said, the main goal of this universal setup is a comprehensive study of polarized and unpolarized gluon content of proton and deuteron at Nika collider at high luminosity. And it will be complementing each other main probes to reach this goal. Charmonia and higher states of Charmonia, J psi, J psi prime, and other states, open charm, and also direct photons in inclusive and semi-inclusive modes. So we expect that SPD can reveal significant insights on gluon helicity structure of proton and deuteron, also unpolarized PDF at high X, which has at the moment large uncertainties, will be studied in proton and deuteron. Also, for the first time, can be measured gluon transversity in deuteron. And at the initial stage of data taking, can be also fulfilled, completed comprehensive physics program, which can be done even at reduced energy and luminosity. So the physics paper, which already published, so this is the reference, and upper reference and lower reference. It's a paper which appeared soon. So the second is just related with the first stage of the Nika collider operation. So SPD physics is related with 3D structure, partonic structure of nucleon. So deep inelastic scattering and high energy collision, they started from inclusive one particle, one variable, scaling variable function. So one-dimensional structure functions. So it used to be proved collinear factorization for parton distributions and partonic scattering. And also later it was generalized for so-called generalized parton distribution when position in impact space is involved. So it's three-dimensional pictures, and also in momentum space, so-called transverse momentum dependent parton distribution function, when we have dependence not only from X, but also from K-perp transverse momentum. So how it's related with structure of proton distribution. Also, we know that 90% of the proton comes from the gluon interaction. Only 10% comes from the mass of quarks, which receive due to Brout and Glare Higgs mechanism of spontaneous breaking in standard model. So 90% of the proton comes from the gluon interaction. We know this from end of 70s. So the visible matter mass actually it comes from protons. So we have to understand how it is, how protons have such mass from gluon interaction. So theoretically, as I said, we had earlier one-dimensional parton distributions which were integrated over transverse momentum. Of course, it was also logarithmic Q-square evolution, so-called Gribov-Lipatov-Altarelli-Parisi, LXXI evolution equations, or in other language, normalization group equations. And now we extend this to three-dimensional distributions. One of them, as I already mentioned, generalized parton distributions, where involved space impact parameter, and other distributions, so-called unintegrated over K-perp PDF. Actually, there are two at the moment approaches which describe these functions. One of them based on unintegrated collinear parton distribution functions, and another is transverse momentum distribution, which is based on factorization over transverse momentum distribution. They are similar. I won't make difference between them. So suppose in general nucleon with momentum p and spin polarization, which can be longitudinal or transverse or averaged unpolarized averaged spin polarization. So we can have a new information, for example, for quark transverse momentum distribution of nucleon. So functions, transverse momentum distribution of quarks, they can be divided into two parts which contain time-even functions and time-odd functions. So there is several classified distributions which related with different symmetries for polarized case depending from longitudinal or transverse polarization. And these functions, they are has some specific names. So, for example, longitudinally polarized quarks in longitudinally polarized nucleon, they have functions which call helicity distribution functions, etc. Or, for example, T-polarized, transverse polarized quarks and T-polarized nucleon, they have, they call pretzelosity. It's from pretzels, like some cookies. And time-odd functions, they reflect spin orbital correlation inside of nucleon or nucleus. So there is a extra special functions which are called by names of the people who discovered it, Sievers and Boyer-Mulders. So if we integrate over K-perp, we can find relation with our earlier one-dimensional Parton distribution functions, which are also measured, for example, in experiments I already shown. So at the moment, I will discuss later, which is what we have now. And we can classify this in these functions in the table. And this this column mentioned notations for polarization of nucleon, and here polarization state of quarks. So this different combination, how quarks polarized, they can be transverse polarized in longitudinal polarized nucleon, and vice versa, depends from the symmetry, etc. But for gluon, there is some complications. And for example, there is no gluon transversity functions, transversity related with the spin orbital, because it's later maybe I will tell, because it's related with spin flip, with spin change 2, and in fermion nucleon we cannot have this change by spin 2, and we can do this only in deuteron. So gluon transversity can be only in deuteron. How we will measure these functions? For example, one of the most sensitive gluon probes, it's Charmonia, open charm, and also direct photons were involved gluon distribution functions. So here shown the different cross-section for Charmonia, higher states, and open charm as a function of the square root of S. I remind you that SPD will work from few GeV to 27 GeV of square root of S. This range of X, which will be sensitive with these probes. So as we know, this PDFs, the functions of X and Q square. So this blue area is expected to be covered by Nika SPD. So for example, Phoenix with higher Q squared in this range. After LHC will cover this region, but it is expected after 2030 if will be approved, because LHC at least until 2030 is already scheduled. And different experiments also, deep and elastic scattering, EMC, SMC. So they, of course, at lower Q square, but they can reach some smaller axes. For polarized distribution, for example, here shown quark and gluon helicity pattern distribution functions. This for quarks, this for U quarks, this for down quarks, this for strange quarks, and this is for gluons. So longitudinally polarized or gluon helicity PDFs, you see the uncertainty for them very high. So SPD is expected to improve this, reduce this uncertainty. And this is gluon transversity of deuteron. As I said, transversity comes from the spin flip, spin orbital interaction, and transition with change of 2 is forbidden for spin 1/2 like nucleon at leading order. And higher orders can be such flips, but spin flips, but it will be suppressed by higher orders. So we expect that gluon transversity in nucleon will be close to 0. Of course, SPD will measure it because we know we could have some surprises, but definitely it could be interesting to see deuteron gluon transversity. We know that in deuteron can be non-nucleonic degrees of freedom, colored forces, hidden color, etc., etc. So gluons which cannot be in nucleon state of deuteron can be measured with this observable gluon transversity. Here, estimation in some models, which could be measured, for example, in study of lepton pairs. One of the well-known problem, it's a so-called spin crisis of proton, when first EMC and then confirmed by SMC and others, that spin of the proton not fulfilled by valence quarks, but actually neither valence, neither C quarks. So people study gluon contribution, but of course this delta G is integral of this helicity PDF, and integral comes from 0. Of course, in data we cannot have a 0, we have x minimum. And for different kinematics, it's a different contribution. So people still try to measure this integral with non-zero lower limit. So here again shown the range of the SPD and how we could reduce uncertainties of this helicity gluon function, which is important to describe spin of proton. And for example, for different lower limits, we show the expected results. And one of the main SPD features that SPD can have better accuracy than other calibration at large X. So we expect mostly to reduce uncertainty at large X, which is also important. Another problem is to see this transverse momentum distribution effects from gluons, because we know at large PT, actually we can use one-dimensional parton distributions. Actually, it's enough with a high accuracy, but at smaller Q square or PT, we have to use this transverse momentum distribution functions. One-dimensional distributions are not enough. So we have different theoretical description of these two different asymptotics, and of course, overlapping imaging area can bring some interesting things, because it can be maybe non-trivial matching. So it should be measured and theory get interesting input from these measurements. These measurements can be done, for example, just to measure left-right asymmetry of differently polarized nucleons. And here, in hadronic collisions, we can have contribution not only from parton distribution, but also from fragmentations of partons to hadrons. So it's also interesting physics. Gluon Sears functions at the moment, it used to be measured at first moment and K perp moment, this gluon Sears function. Here shown the results of Phoenix, and where we expect results from SPD. At Nika energies, we had only measurements, old measurements, more than 30 years ago, and started more than 30 years ago, published in 95. It's experiment at fixed target, protons with 200 GeV. So it was first indication that this asymmetry can be non-zero, and in this energy, SPD will check it with high precision, because we will have, I think, at least 2 or 3 orders magnitude higher statistics and better detector. So other available results for asymmetry, this is mostly from Phoenix at high energy, at high energy and small x. But you see that uncertainties are large, so we expect that we can improve this, reduce these uncertainties. So expected results for effects induced by in TMDs with different probes, with gammas, direct photons, with open charm d mesons, and also with charmonium. So at the initial stage, also SPD physics program is very rich. Spin effects, among them, it will be studied spin effects in PP, PD, and DD for elastic and quasi-elastic scattering in different kinematics. Spin effects in hyperon inclusive production also can be studied multi-quark correlations or short-range correlations in neutron and light nuclei. It will be searched for different dibarion resonances and other exotic resonances. Hypernucleus productions will be studied. Also, near threshold, we could study open charm and charmonia production. At large PT hadron production, we can study diquark substructure of proton. In semi-inclusive large PT hadron production, we can study multi-parton scattering when simultaneously several partons from one proton can collide with several partons from other proton. And also some measurements which are related with, for example, astrophysics and beyond standard model searches. For example, anti-proton production measurement can be important for explanation of the results like alpha detector in International Space Station, and measurements which like transversity can be important for BSM search, because BSM contributions can give contributions through this observable to the such values, such observables like electric dipole moment of neutron, etc., etc. So I come to my summary. So SPD physics detector, a universal setup at Nika Collider, which designed for comprehensive study of polarized and unpolarized gluon content of proton and neutron in both polarized and unpolarized high luminosity modes of PP and DD collisions with square root up to 27 GeV. Main probes which complementing to each other: charmonia, open charm, and direct photons. So we expect that SPD can reveal significant insights toward three-dimensional gluon structure of proton and neutron. Also, we'll measure with higher precision gluon PDFs at high values of scaling variable X and proton and neutron. And also, for the first time, we'll measure gluon transversity in neutron. And will be also comprehensive and rich physics program for the first and other period of data taking. And as I mentioned, SPD physics program is complementary to the other intentions to study gluon content of protons and nuclei at RIC after LHC, spin, electron ion collider, and also meson. in Compass++, Amber, and also at Electron Ion Collider. And here references for SPD CDR and SPD physics papers. Thank you for your attention.
Thank you very much, Victor. Thank you very much for the nice presentation. And I see the question, please.
Yes, can you hear me?
Yes, yes, very well.
Okay, yeah. So thank you, Victor, for this presentation. And I have a rather general question. So at the beginning of your talk, you said that there won't be hardware trigger. So my question is, do you plan maybe to do some kind of machine learning or artificial intelligence to use it as a software trigger?
It will be not trigger, it will be online filter. So we have buffer which consume all the, I think I shown.
Yeah, but this buffer, would it be based on some conventional
input buffer? It's will be consuming all the information which collected by the SPD detector. But for writing, before writing, will be used special online filter, and this filter will use all these neural networks, machine learning, and artificial intelligence, etc., and also natural intelligence.
Yeah,
so,
I mean, yeah.
And this filter will divide in several flows, and approximately it will reduce maybe 1 order of magnitude the initial flow.
Okay, yeah. Thanks.
Okay, thank you, Alexei. Other questions?
I mentioned the data rate already after this online filter.
Very good. Please, colleague, feel free to ask Victor about very interesting physics and spin physics detector. Okay, if no question, thanks again, Victor, for the nice presentation. And now 12 o'clock in Petersburg, the cannon has already shooted, and we are with great pleasure inviting our friend from, our colleague from the G-Sites, scientific director of Helmholtz-Zentrum für schwere Ionenforschung, the Paolo Giubellino. Paolo, we are happy that you with our conference, and please.
Hello, dear colleagues. Unfortunately, I'm in an airport and there was no way to find a corner protected from the loudspeakers.
Okay,
so,
doesn't matter.
From time to time, you will get this background. I will maybe mute for a second to spare you the announcements. So I will, and now let's see if the screen shares properly.
Okay, we can see your screen.
Wait, not yet. Okay, so that.
Yeah, now
okay.
It's full screen. Yeah.
Do you see the slides changing?
Yes, very well.
Okay, so we can start.
Yes.
And let's hope that the loudspeakers will not be too frequent. so it's a great pleasure to see. Hello?
Yes, Paolo, we can hear you.
There's something strange on this slide.
We can see your slides and we can hear.
Yes, but it is not changing.
It's not changing.
I'm trying to move to the following slide and it does not want to.
Oh.
My goodness. Let me get out of this. Sorry.
But we can share for you if you want. And
do you have my slides I sent?
No.
I think so no. Then let me just stop share and retry. Sorry.
No problem. Yeah, we have a time and before the lunch. And
I apologize, and let me try to see. Ok, subito, solo che let me try to, I put it in, I make a PDF so that it's not as big, and moreover, they are forcing change corner.
Okay.
This was the quietest corner I could find, and of course they tell me that it's not allowed to sit there. Okay, so I'm moving to a different corner. Sorry, this is really a bit ridiculous.
Yeah, it's real life.
You will bear with me. I try to be quick. And see. In the meantime, the computer is saving the PDF. And I reach apologies to my hands. So let's see if I now manage to. We are almost there.
Yes. Yeah, don't worry, we have a time. And
I also can stay a little longer.
Okay.
But let's see if this manages to finish. It's almost done.
Si ricorda che al fine di evitare assembramenti all'interno dell'aeroporto occorre mantenere il distanziamento sociale e rispettare la distanza di 20 metri dalle altre persone. We remind you that in order to avoid crowds, social distancing must be maintained inside the airport, and a distance of at least 1 meter away from others must be respected.
Okay, let's try now with the PDF to see if this will be more efficient. Okay, new test. Okay, and let's see.
Yes, we can see your slides.
Okay, if you can see the slides, then
yes.
We go. Okay.
Very well. Yeah.
Dear colleagues, sorry for all these technical issues. We live in a very, very interesting moment because it's something which has been obvious all along, that is that what drives all the main processes that somehow define the way our universe looks like, starting from the burning of the sun near us, they are all nuclear processes. So what is very important is to remember that nuclear physics has been always the science that has driven our understanding of the universe evolution. You have heard just earlier today the presentation about the Alice experiment, which looks at the very early phases of the evolution of the universe after the Big Bang. But there's many experiments that look at different moments in the history of the universe, which has made big jumps recently, thanks to colleagues in the observation of the universe. On one side, the emerging of experiments which are capable of measuring gravitational waves, but also on the study of neutrinos, that with experiments like IceCube have become now really a major observational tool, and the overall multi-messenger astronomy that looks at the universe with combinations of different instrumentation. So you have the nuclear physics on one side, the observation of the universe on the other, and the big development of the theoretical tools that work together in making us live through a fantastic era of better understanding of the universe. As you know, GSI is an historic laboratory. We have more than 50 years now. Actually, I have to correct this slide. It's over 50 years. It's now 51. And it's a large laboratory that has been one of the drivers in Europe. If you look at the table of the elements, 6 of the elements have been discovered at GSI. It's the table of the isotopes here. All the red ones have been discovered at GSI. So you see the black ones are the stable elements, isotopes. And the further away you go from this line of stability, the more recent are the discoveries. And you can see that basically the recent discoveries of new isotopes have been largely made at GSI. And but also one of the things that we are very proud of is been the development of cancer therapy with nuclear beams that is now being established as a clinical process. So we have pushed it out to clinics where it is performed in a systematic way, but it's still a major subject of developments. You will see it later. And also, in the end, let's remember, science is done by brains, it's done by people. And we are very, very proud of our capability to work as a talent factory, as an infrastructure that creates a proper environment for young people to develop their talents and to grow. And if you consider that we have more than 300 doctoral students, for example, this is really large numbers. And also, there's a lot of students which come through programs like Get Involved that we have now developed in the last few years as a training and instruction place. So if you look, I don't know if you see my cursor, but up left in this photograph, in this picture, is GSI, and all the rest of the picture is occupied by the FAIR facility, which is now under construction. While GSI, that I was describing before, is a German laboratory, for FAIR, there is a different scheme. It is the national laboratory that is owned by a consortium of countries. And you see the flags down here. And in particular, and let me silent for a second while they finish the announcement. So what is very important is that in particular, Russia has a leading role here, not only because it's been one of the key countries in terms of financing, is the second largest after Germany, but because of the intellectual and technological contributions, there are entire accelerators which are completely built in Russia and then brought to the site. And there's also a major role in the experiments. This is looking at FAIR from the international collaboration point of view. So there's 9 shareholders that are the ones in dark orange. and associated and aspirant partners that are light orange, and countries which have agreements to participate in the experiments, which are the blue ones. There are approximately 3,000 scientists involved. And as I was saying before, Russia is the largest shareholder of FAIR after Germany, but also is a major involvement in the construction and in the design first, and now in the construction of the accelerators and of the experiments. And you see here the many institutions throughout Russia that are involved in FAIR. So now if you look at more schematically, up left is GSI, as I was saying before, with blue are the accelerators of GSI. And in the red circle is FAIR, which is now under construction. FAIR, what makes FAIR special is the frontier of intensity, so the intensities of the beams, the capability to accelerate essentially any beam, and then have a system which is called the fragment separator, which allows to separate out from after a collision with a target specific isotopes and then do experiments with them. And last but not least, very important factor, what makes this whole infrastructure special are its accumulation storage rings that allow the performance of very high precision experiments by recirculating beams of rare isotopes. There are two families. One is on the GSI side, which are the low energy ones, but they are fully integrated in FAIR, and the higher energy ones, which are on down here, the HESR and the CR. The science of FAIR is structured in four so-called pillars. APA, which is dedicated to atomic physics, biophysics, plasma physics, and material research. CBM, which is nuclear and core matter, which provides, which follows the exploration of the phase diagram of strongly interacting matter in the region of high densities and high compression. This is a complementary experiment to what is done in NICA. NICA works in collider mode. This is fixed target mode. So here one can get higher luminosities. In NICA, one gets all the advantages of operating in the center of mass. So they are completely complementary in their science. NuSTAR is an experiment, a family of experiments which deal with the nuclear structure and nuclear astrophysics. Last but not least, PANDA is an experiment which will use antimatter. One of the secondary beams that you can produce is actually antiprotons. So what will have antimatter used is a tool to study the structure of hadrons and their interactions. So when we refer to FAIR as the universe in the lab, what we refer to is the fact that FAIR will allow to perform in controlled conditions in the laboratory experiments that reproduce some of the fundamental processes that govern the evolution of the universe. One extremely important one is, for example, the production of the heavy chemical elements like gold and lead that are produced in extreme events like the merger of neutron stars, and that here will be reproduced and studied in all its aspects. In APA, you will study the extreme electromagnetic fields involved. Then in CBM, you will study the equation of state of the neutron star and then of the merger of the neutron stars. At the exact energy densities and temperatures that are happen in these processes. And then you will follow up the production of the hadrons, and last, the evolution of the produced nuclei that will mostly be exotic, highly neutron-rich nuclei, and their decay to populate the periodic table as we know it. But there are many, many others. I will not mention many. There is one which is in course now, for example, which goes to measure a process that allows us to measure what has been the average luminosity of the sun throughout its life by measuring the effect that the neutrinos impinging on the Earth have had on the abundance of certain minerals. But another one is the studies, the building blocks of life, the production of carbon and oxygen in stars. You know that a star like the sun burns hydrogen to make helium, but then you can burn helium to make carbon, and carbon plus helium to give oxygen. But how much oxygen, with what rate, you have to measure these cross sections, and they are very poorly known. Actually, this was indicated already in his acceptance talk for the Nobel Prize in 1983 by Fowler as one of the most fascinating processes to be studied. Well, it has taken 40 years to get there, but we are now finally measuring it. And also, we take all these beautiful pictures of planets, but the inside of planets, even of our own Earth, is largely not understood. And the study of plasmas, very high energies, will open a window on our understanding of planetary science. And also there are a lot of technological applications. Of course, one of which we are very proud is our computing developments, which have allowed us to create what's called the green IT cube, which is in the sense that it is one of the computer centers in the world. At the time, actually, of its completion, was the most energy efficient. It's still one of the most energy efficient, with this completely innovative approach to the cooling of computers. But we have a huge program linked to space. You know that space travel now is more and more popular, and it goes towards long trips, going to the Mars, for example. But there, as you know, the travelers and all the equipment are exposed to a very high level of radiation, and one has to study the effects in order to be able to mitigate them, both on people and on devices. And for that, ESA, the European Space Agency, has selected FAIR as its long-term partner as a ground laboratory for radiation studies. Actually, we have, for example, a joint summer school event. But we continue developing medical applications. I will say a bit more in a minute. And also many other things like the development of nuclear clocks that are becoming increasingly interesting because of the need to improve the precision of satellite-based location system. I mean, the GPS that you have in your phone has as a precision of a few meters, as you know, and the main limitation of that is due to the precision of atomic clocks. And going to nuclear clocks, you can improve by something like an order of magnitude or even 2, and that would allow, of course, for a much more extended use of GPS for example, self-driving devices. So, how is the construction going? The construction is going extremely well. In May, we have closed the CIS-100 tunnel. So the construction of the largest of our accelerators, let me remind you, look at the picture. So this one up here is the largest of our accelerators. structure is, the civil construction is finished, and is now progressing in the rest of the site. Components are accumulating. For example, all the dipoles and the RF cavities have been delivered. Quadrupoles are coming, and other components are coming. And you see, this is the construction site. You see that CIS-100 at the back is completely filled. And we are now working on the southern side. This is on the left is the transfer building, of which the beams will, from which the beams will come from GSI to FAIR. And to the right is the southern set of buildings. And of course, contextually, the experiment, it's a group of very noisy people. So also the experiments are progressing. You can see here, for example, down at the right, the magnet of Panda. It's a huge magnet that is now ready for shipment from Russia. The CBM components under test. This down here in upper is the result of our so-called prior, our proton microscope that we use to study plasmas by doing a radiography with a proton beam. Now, so you've seen the construction of the site. It goes on very fast. We're very, very happy about it. So what happens next? The experiments will start. As you can imagine, since the construction is ongoing, they will only start around 2025, 2026. So how do we get there? How do we develop our know-how? How we develop the capability to operate the accelerators? And especially how do we develop the scientific community? And what we have is a precursor program, which is called FAIR Phase 0, which runs about 3 months per year, which progressively puts in use whatever is available in terms of experimental equipment and accelerators for FAIR, and develops at the same time frontier experiments. So this is how this program looks like. Each green arrow is an experimental area. And there are more than 1,000 scientists involved in this program, which basically has calls. And as an international competition, we actually have a request for about 3 times as much beam time as we are able to offer. So there is a lot of demand for these experiments. And there we have therefore a very rich program that, by the way, exploits extensively the fact that at GSI and FAIR, you can run experiments in parallel. So we have 6 or 7 experiments at the same time. So although it's only 3 months of beam time, we actually managed to perform a large number of experiments, about 56 experiments per year. And you can see these were the requested shifts, and these are what we are able to allocate. And you can see that the demand is very, very high. It's about 2 to 3 times what we can actually offer. So this is the accelerator complex as it is now for FAIR Phase 0, which is basically mostly accelerators which were already part of GSI, plus Cryring, which is new. It is there for FAIR. And we have basically been able progressively year after year to put back into operation all of this and increase the intensities and the performance of the overall setup. And these are just a couple of results from experiments ongoing as part of this FAIR Phase 0 program. I told you about prior. Now you can see it better. If you take a watch we have done with the previous version of this proton microscope, and you can see the relatively modest resolution, and to the right, the amazing resolution that you can have with the new FAIR proton microscopes. CBM, remember the experiment on high density nuclear matter, has developed what's called the mini CBM, which is like a slice of the future mini CBM, but with all of the detectors present. And they have managed now to test CBM in its full speed. That is the key factor for the experiment. I just mentioned a couple of, for example, this experiment to the up left in this picture is how the evolution of the therapy with nuclear beams brings us to new ideas. This is the first picture taken by doing therapy with a radioactive beam. And why that's interesting? Because you can get in real time a PET of the irradiated tumor, so that you can have what is called theranostics, in the sense that you can do diagnostics, you can do the observation of the tumor in real time, in vivo, during the therapy. This is
buongiorno, partenza del volo KL
stop for a second because it's very noisy.
Per ragioni di sicurezza si presentavano. A nome di Alfanze, KL Nascetti, mega buon viaggio.
So
Ladies and gentlemen, good morning, departure flight QLM flight 1556 for
I don't know if you can hear anything now with the loudspeaker, but okay, I'll try to continue anyway, hoping that you can
yes, good.
hear something. You see down here the Panda experiment that has already a number of detectors ready, and so they have installed them in another setup, which is the setup of Hades, so that one can do a joint experiment of Panda and Hades with the proton beam right now. So what's the future? The future is that we keep receiving a lot of demands for beam time. This comforts us with the fact that this is very interesting. And so we will continue regular beam time allocations every year until fair operation can start. And so we developed an integrated plan of continuous improvement so that there will be a continuous development of the program until fair is started. So we look forward to very exciting science already in these coming years. And I wish you a very, very interesting conference. And I really apologize for the loudspeakers, but they limit access to the various areas of the airport. So I could only find this as a quasi-quiet place.
Okay, Paolo, thank you very much. Yeah, it's very impressive that you are connected with us, and thank you very much for the nice presentation. Okay, maybe some people have questions. Please feel free.
May I ask?
Yes, Stepan.
Paola, may you say some words about the plan for the HISR and Panda? And questions, second one, is it possible use the cis-18 beam for zero phase of the Panda working?
Okay, so I first answer the second because it's quicker. For some elements of Panda will be used for experiments together with others, but for the actual Panda program, one needs the cis-100 because the cross-section for anti-proton production at cis-18 energies is too low. So you would not get any intensity of anti-protons. Actually, we looked into that, if there would be any way to get anti-protons for Panda already with cis-18 beams, but no, you need to have the cis-100 ones. As for the construction of the HESR, the accelerator is practically finished, and for the CR, the magnets are coming. So the progress is very good. Where we have an issue is for the civil construction of the buildings, which are not very complicated buildings, but there is still no commitment of funding from some of the shareholders that would allow finishing this construction. We hope that this will happen very soon. At the moment, since the construction of these buildings is decoupled from the rest, even if that would start in a year from now, they would still come in time to start with the others. And the accelerators are actually even more advanced. So we have to keep pushing to get commitments to get the funding to complete them. But honestly, I have no doubt that it will happen. I mean, the accelerators are practically ready. So to leave them in a warehouse and not install them because of the lack of civil engineering, it would be really, I don't know. I don't think this will happen. So, but some money is still missing. So we have to hope to get these commitments soon. As of today, there would still be enough time to finish these buildings in time to get the beams from CIS-100 when it's ready. We have I think it would take too long to find it now, but we have redone the overall planning of the construction of FAIR only a few months ago. And from the technical point of view, we would be able to complete everything at the same time shortly in 2026, 2027. But there is still a shortfall of money. And we have to keep working on our funding agencies to convince them to commit. So I hope also the scientists in Russia will also make pressure towards because also Russia has still a commitment to make for part of the money, and it would of course help a lot.
Okay, thank you, Paula. More questions, please, colleagues.
Comment?
Sorry.
Hello.
No, yeah, Grigory, please.
Hello, Gregory.
Yes. Hello. Paulo, it's really a great pleasure to see you, and thanks a lot for your interesting and very encouraging for us talk, because the progress is really in various fields that you've shown. It's really impressive, and I must say that we were really very lucky almost 30 years ago to meet you and to work together, because it was a very efficient cooperation, and you've shown us a very nice example of a great fighter. Also in this conference, you came over all these problems, but I must recall that starting with Alice from scratch, really from scratch in '92, and we were really very efficient. So I think we could be really consider ourselves as lucky guys to meet you and to work together for many years. So thanks a lot for your presentations, and we're very glad to see you. We hope to see you once here in St. Petersburg in person.
Absolutely, I would be more than delighted to come again. I mean, let's hope that this is the last time we have a conference virtually, and we will be able to.
So we hope to keep in touch. We are flying in parallel with the speed of light, practically. Let's hope we meet one day. Okay, thanks a lot. Thanks a lot.
Thank you to you, and I wish you a very, very good conference. And looking forward to see you very soon. I'll go get my plane.
Okay,
ciao.
Thank you, ciao, Paolo. Yeah, thank you very much.
Bye-bye.
Okay, bye. And now I have two announcements from the organizing committee. now we are starting for lunch, and we will see again for the session meetings at 1:35. And second one, we have a book of the abstract in our website. Please read it, and thank you very much for the all speakers in the morning plenary session. Yeah, thank you very much, and we will see tomorrow on plenary. It will be interesting session with neutrino experiments, and we will see after the lunch. Thank you.
До свидания, Наталья.
До свидания. Спасибо, Наталья.
Ну, это было несложно. Спасибо вам.
Спасибо вам.
Спасибо. Все хорошо. Удачи.
Спасибо.
Спасибо. До свидания.